Hello, and welcome to Game Optimization with the AMD Radeon Developer Tool Suite. I'm Chris Hessick from the AMD Developer Tools team, and I will be joined today by my colleague Amit Malay. In this presentation, Amit and I will give a brief introduction to each of the tools included in the suite. Then we will talk about some of the new and upcoming features in each of the tools. First up, we have the Radeon Developer Panel, or RDP. This is the tool that is used to collect data from a running application for use with the other tools in the suite. The Radeon GPU Profiler, or RGP, is a runtime profiler that uses information from the GPU hardware and graphics driver to help discover optimization opportunities in a game. Radeon GPU Analyzer, or RGA, is our offline compiler and code analysis tool. Radeon Memory Visualizer, or RMV, is a tool to help analyze an application's video memory usage. Radeon Ray Tracing Analyzer, or RRA, is designed to help improve ray tracing performance by analyzing a game's use of acceleration structures and ray dispatches. Finally, we have the newest tool in the suite, the Radeon GPU Detective, or RGD, which is a tool used for post-mortem analysis of GPU crashes. Let's now look at the releases of the suite since last year's GDC. In April, we introduced new versions of the tools, which included some of the features that we spoke about at last year's conference. In August, we were very proud to release the first version of the Radeon GPU Detective, with support for DX12 crash analysis. September saw a release of the full suite, including support in RMV for loading and analyzing crash dumps generated by RGD. And finally, in December, we launched new versions of all tools, including version 2.0 of RGP and version 1.1 of RGD, which added Vulkan support. We'll now take a closer look at each of these tools. Let's start with the Radeon Developer Panel, or RDP. The panel is the way that a developer interacts with the driver to extract data from a game. That data can then be analyzed and visualized in each of the tools in the suite. The panel is the first interaction most developers will have with the Radeon Developer Tool Suite. Over the years, we have added new tools to the suite, and each existing tool has added more features. This has caused the panel to become more and more complex. It can be a bit daunting for new users to understand where in the panel they should start. In an effort to improve the new user experience and to simplify the workflow for existing users, we are in the process of redesigning the user interface and workflows in RDP. Here you can see a screenshot of the new UI, which will be called RDP version 3.0. Instead of needing to visit different tabs within the UI to set up and initiate data capture, everything needed to configure and capture data can be found in one place. As an example, if you're using the panel to capture profiling data, you no longer need to set up the profiling workflow separately from the capture UI. The early feedback we have received from beta users of this new UI has been positive, and we hope to release it publicly soon. We'll now move on to the Radeon GPU Profiler, or RGP. Let's start by looking at some of the major UI changes introduced in version 2.0. If you're an existing user of RGP, one of the first things you may notice in RGP 2.0 is the new layout of the wavefront occupancy view. Here's a screenshot of the original wavefront occupancy UI as seen in RGP 1.16 and earlier. Formerly, the UI elements to interact with each row, as well as the legend corresponding to each row, were shown above and below the corresponding row. And here are the changes introduced in RGP 2.0. As you can see, the individual rows are now packed tightly vertically with no margins between them. And the UI elements and legends have been moved to a panel on the left side of the rows. This gives us more vertical real estate to view the important data that gives insight into a game's performance. The new left-hand side panel can also be hidden in order to give even more screen real estate to the visual data. In addition, you now have control over which rows are shown, as well as the vertical ordering of the rows. This allows you to customize the view for your specific need. So if, for example, you do not want to see the counter rows, you can hide them by simply clicking the X button next to the row. Here we have hidden the ray tracing counter row. To make the row visible again, you can use the Views combo box that appears above all the rows. This combo box can be used to toggle any row on or off. You can also drag a row to a new position. So if you want to see the event timeline right below the wavefront timeline, you can quickly do that. To change the position of a row, you can simply move the mouse over the drag icon that appears to the left of the row that you want to move. Once the mouse is over that icon, a blue dashed outline will appear to let you know which part of the UI will be moved. You can now click and drag the row to a new position. As you are dragging, a blue solid line indicator will appear to let you know where the row will be moved to when you let go of the mouse button. When you are satisfied with the new position, simply release the mouse button and the row will appear in the new location. Here we have moved the cache counters row to the bottom of the view. Any changes you make to the layout will be saved when you close down RGP, and they will be reloaded the next time you run. If at any time you want to revert back to the default layout, there is a Restore to Default button. Simply click that and any changes made will be undone and the default layout will be used. While these changes to the wayfront occupancy view are hopefully useful in and of themselves, they really serve to unlock some plans that we have for additional data to be shown in this view. Stay tuned to GPUopen.com to learn about these additional features when they become available. Next, we'll take a quick look at the new dark mode support introduced in RGP 2.0. By default, RGP will still use the same light mode color theme that it has always used. However, for anyone who prefers a darker color scheme, RGP can now be told to use a dark theme. Or it can be told to use the same theme used by the host operating system. Here we can see what RGP looks like when using dark mode. To switch between themes, or to tell RGP to follow the OS theme, simply visit the Themes and Colors setting page, and use the color theme combo box that can be found there. In addition to these UI features, RGP 2.0 also introduced a feature to help you understand thread divergence in a ray tracing pipeline. The Radeon Developer Panel has a new checkbox that enables internal shader instrumentation at runtime. This extra instrumentation allows RGP to determine how many threads are active each time a shader function that is part of the ray tracing pipeline is called. RGP is able to summarize this data in the ray tracing shader table, where a new column appears that shows the average number of active lanes across all calls to each shader function. This can give you an indication of how much thread divergence your ray tracing pipeline is experiencing. If you move the mouse over one of the values in this column, a tooltip will appear, displaying a histogram that lets you know how the number of active lanes is distributed for all invocations of a given shader function. As mentioned, in order to use this feature, you must enable shader instrumentation prior to capturing profiling data in the Radeon Developer Panel. We don't enable this by default because the instrumentation can introduce additional overhead in the running application. Here we can see a screenshot showing where this checkbox can be found in RDP 2.12. RGP also has support for work graphs, which is a recently added feature in the DirectX API. When you profile an application that dispatches a work graph, you will see additional events in RGP's event list. Here we can see that each sub-dispatch from the graph is represented as a separate event. This lets us see how the work is being broken down during work graph execution. We can also see some of the setup work that is performed to initialize backing memory used by the work graph. Additionally, by asking RGP to color the wavefronts in the event timeline by the event, you can easily see which waves come from which graph sub-dispatches. We have some exciting future plans for additional support for work graphs in RGP. Please stay tuned to GPUopen.com for any announcements about this future support. Now let's switch gears a bit and take a look at some new features in the Radeon GPU Analyzer, our offline compiler and code analysis tool. In the most recent release of RGA, we added a new binary analysis mode, which allows you to disassemble and analyze pre-compiled AMD GPU code object binaries. To use this new mode, run the RGA GUI app and select the binary analysis mode on startup. You can confirm that you are in this new mode by checking the status bar. In addition to showing the active mode, it will change to a purple color to indicate binary analysis mode is active. If RGA is running with a different mode active, you can use this lower pane to switch to binary analysis mode. Once you are in this mode, you can simply drag any file which contains a precompiled AMD GPU code object binary and drop it right onto RGA. RGA will then load the binary and show a list of shaders and kernels in the pane on the left, and it will show the disassembled ISA for the selected shader or kernel in the pane on the right. Also displayed in this ISA disassembly is a visualization of the VGPR pressure for the selected shader or kernel. This new mode is designed to fit into a developer's existing workflow. So if you're a HIP or an OpenCL developer and you normally edit and compile your kernels in an IDE, RGA can seamlessly work with that workflow. Simply load the compiled binary from your project's output directory, and each time you recompile it in your IDE, RGA will recognize that the binary has been updated on disk and notify you that the output will be reloaded and reanalyzed by RGA. Before moving on from binary analysis mode, I want to mention an upcoming RGP feature that will take advantage of this capability. This is not yet available in current RGP builds, but we plan to release it later this year. A request we have received from developers is to allow RGP users to easily take advantage of some of the analysis features in RGA. To support this, we will allow pipeline binaries to be exported from RGP and will automatically load them into RGA for analysis. One use case for this is to use RGP to identify an event whose shader achieves low occupancy, where RGP indicates that the limiting factor for that event is its use of vector registers. With this new feature, you will be able to quickly open that pipeline in RGA and use the live register analysis feature to better understand how the shader is using allocated registers. This could facilitate finding a way to reduce the number of registers used and potentially increase the overall occupancy of any event that uses the pipeline. To support this, anywhere in the RGP user interface where you can select an event or a pipeline, you will be able to right-click and ask RGP to open RGA to analyze the pipeline. When you select this new menu item, RGP will extract the pipeline binary from the loaded dataset and launch a new instance of RGA, passing the extracted pipeline to RGA for analysis. Next, I want to show a preview of a new feature we are adding to a future RGA release. This feature allows DX12 developers to compile a standalone vertex, pixel, or compute shader without requiring a complete pipeline. In the current RGA release, a whole pipeline is required. For graphics, this means you need to provide at least a vertex shader, a pixel shader, a pipeline state object, and a root signature. But what happens when you don't have one of the shaders? Or if you are missing the root signature or the graphics pipeline state? This new mode will auto-generate the missing pieces of the pipeline for you using reflection. Let's consider an example, compiling a single pixel shader without a vertex shader, without a root signature, and without a file containing the graphics pipeline state. In terms of the command line invocation, there is no change to how you use the tool. You use the same RGA DX12 commands as before while omitting the missing pieces of the pipeline. RGA will detect that parts of the pipeline are missing and auto-generate them. Here you can see the HLSL code of an auto-generated vertex shader. RGA will generate a text-based representation of the root signature. That way you can investigate any compilation issues that may come up. Here you can see the auto-generated root signature for our example. And similarly, here you can see the auto-generated GPSO file containing the graphics pipeline state object. All of the auto-generated files will match with the provided pixel shader in terms of the vertex attributes and the resource bindings. Upon successful compilation, you get the result, pixel shader disassembly. So, let's quickly review the compilation workflow. We started with the pixel shader HLSL file. RGA used reflection to generate the vertex shader, the graphics pipeline state in a GPSO file, and the root signature. The AMD shader compiler was invoked, passing in the provided pixel shader and the auto-generated files. The compiler and RGA then produce the expected output files. This feature will make RGA's DX12 mode easier to use than ever before. Please stay tuned to gpuopen.com for more information on this feature when it becomes available. Now, I would like to hand off to Amit Malay to continue our look at additional parts of the tool suite.
Thanks, Chris. Let's talk about the Radeon Ray Tracing Analyzer, or RRA. Last year in September, we updated RRA to version 1.3, which introduced new dispatch features. In order to activate this feature, prior to capturing a scene, you can check the Collect Ray Dispatch Data option in RDP. In some instances, there may be too many rays for us to capture. If that is the case, changing the resolution or the window size of your game may be a quick solution. And if that does not help, you can try increasing the ray dispatch buffer size through the drop-down in RDP. Once you open the scene in RRA, you can navigate to the Ray tab by clicking the tab or by clicking the dispatch cards in overview. If you have a 2D dispatch, the dispatch view should look like this. Here you can see the traversal loop count registered by the traversal algorithm. The real-time traversal counter features in RRA, such as those found in TLAS and BLAS panes, are for the primary ray only, meaning that they only capture a single ray shot from the camera. The ray panel counters, in contrast, capture all the rays in your dispatch. So these counters represent the exact amount of work your dispatch has executed. You can inspect a dispatch indice or a pixel by double-clicking through the image or the list. This will take you to the ray inspector. Here you can see all the rays that have been shot by that pixel and overlaid onto the TLAs of the selected ray. You can also see the ray arguments and the resulting hit information, so this may come in handy in debugging your implementation. With version 1.4, we have also added the ray directions view to the dispatch tab. This feature can help identify shadow and reflection areas quickly. I also want to show a preview of a feature we are working on for the next release of RRA. We'll be updating the inspector view to display the ray hierarchy. In current versions of RRA, rays are listed in order of when they were shot. With this upcoming feature, you will be able to see the recursion of the child and the parent rays. Now, we'll take a look at some recent enhancements to the Radeon Memory Visualizer, or RMV. A number of changes have been made to RMV over the past year to give developers a more accurate view of their memory usage. On the main timeline, in Resource Usage Size view, RMV now includes unbound memory on the timeline graph. The stacked usage types on the timeline have been prioritized to show most important resource types on the bottom and the least important on top. A new algorithm is used to calculate usage sizes of the aliased resources. This is helpful when overlapped resources are bound to the portions of the same virtual allocation memory regions. The memory's usage is only attributed to the resource with the highest priority. For DirectX 12, implicit heap, buffer, and image resources are detected and filtered more reliably through the use of additional data collected while capturing memory traces. Memory bound to the resources created outside of developers' application implicitly are not included in usage calculations. The resource overview pane contains the same memory visualization improvements found on the timeline pane. The resource usage size takes into account aliasing and size the resource block according to the usage algorithm. The tooltip and the resource details show the actual amount of memory used by a resource as well as the size after aliasing. The memory filtering slider has been enhanced to use the logarithmic scale and now displays the lower and upper range values. This updated memory filtering slider is used throughout the RMV user interface panes. Numerous refinements have been made for resource name processing. In addition, named virtual allocations are now displayed when available. These are the additional RMV improvements. The heap overview pane now includes the allocation count and the resource count for each heap type. For the newer traces, CPU and driver information is displayed on the device configuration pane. RMV now uses a file format which allows for compressed files. Users can now take advantage of new hours time unit mode. In this mode, timestamps are formatted as hours, minutes, seconds, and clock cycles. New columns have been added to the resource history table in the resource details pane. Base virtual address are listed for memory allocations and resource bind events. For page table updates, both the physical and virtual addresses and the size of memory that was paged is displayed. That's all about RMV. Now we are excited to showcase Radeon GPU Detective. Radeon GPU Detective, or RGD for short, is a new member of our Radeon Developer Tool Suite. It is a post-mortem crash analysis tool, which means that we set the driver to the crash analysis mode before reproducing the crash. Once the crash is reproduced, the tool generates a crash dump file. From the generated crash dump file, tool produces a concise crash analysis report which helps in narrowing down the search for the crash root cause. This is the minimum system requirements. RGD is supported on Windows 10 and 11. Currently, it supports Radeon RX 6000 and 7000 series GPUs. The minimum driver version required is 23.12.1. RGD has first shipped in August last year, supporting DirectX 12 first, and with December 2023 release, RGD now supports Vulkan as well. Let us look at the tool workflow. Similar to previously discussed tools, using RDP, user first enables the crash analysis mode. While RDP is running in the background, user launches the crashing application. The RDP process detects the newly launched app, and from the crashing app's startup, the tool is tracking all the memory transactions and the command submissions. Once the app crashes, all the tracked information is written to a binary crashdump file. Once the crashdump file is generated, RGD CLI tool runs in the background to generate the crash analysis summary file, where it presents the information that can be helpful for the user to debug the crash and find the culprit. I hope you all are curious to learn more about the tool. If you are, please look at the video titled Postmortem GPU Crash Analysis with AMD Radeon GPU Detective, where we discuss the RGD tool in more detail. That brings us to the end of this presentation. To download the Radeon Developer Tool Suite and watch more videos from the team, please visit gpuopen.com. Thanks for watching to the end, and goodbye from myself and Chris.